Oh, okay. Our next speaker is Neranga Fernando from Knox College, who will talk about reverse Dickson polynomials. Please.
And yeah, thank you. And first of all, I'd like to thank Professor Neddenson for this opportunity. And when I first saw the conference, I wasn't sure if I could submit an abstract based on finite fields. But then I contacted one of my colleagues at CUNY, and she let me know that there are talks on finite fields and the applications. And thank you again for the opportunity. And so today I'll be talking about my contributions to the family of reverse Dickson polynomials. And mainly, I'm going to be talking about the permutation polynomials arising from reverse Dickson polynomials. And the second half of the talk will be based on a recent research project I concluded with two of my students at College of the Holy Cross in Worcester, which was funded by an REU grant. And all right, so what are reverse Dickson polynomials? And before I talk about reverse Dickson polynomials, let me introduce you some notation. I'm sure most of you are familiar with this notation. So let P be a prime and Q a power of P, and FQ denote the finite field with Q elements. And as usual, FQ star denotes the multiplicative group of the finite field FQ. And FQX is the set of polynomials, ring of polynomials whose coefficients are in FQ. And as I said, I'm going to be talking about permutation polynomials over finite fields. So the main question is, what are permutation polynomials? So here's the definition. So they are simply polynomials that permute the element of a finite field. So it is a well-known fact that any function from FQ to FQ can be represented by a polynomial. Can be represented by unique polynomial of degree at most q minus 1. So given an arbitrary function, if you want to find this polynomial, all you have to do is use that Lagrange interpolation. So you can find, so that means studying permutation polynomials over FQ, they are equivalent to studying bijections from FQ to FQ. And so now the permutation polynomials. So when it comes to permutation polynomials, I'm going to talk about the history of permutation polynomials. And the history of permutation polynomials go back to late 1800s. And it was the French mathematician Charles Hermite who first studied permutation polynomials over finite prime fields. And then it was the American mathematician Leonard Eugene Dickson who studied permutation polynomials over finite arbitrary fields while he was a PhD student at the University of Chicago in the 1890s. So this is the family of polynomials he studied. Now we can define everything nicely. So as you see that I have said that this is the Dickson polynomial of the first kind. So I'll explain why we call it the first kind soon. And here, the Dickson polynomial, n is the index, and x is a variable, a is a fixed parameter in the finite field. So this is the explicit expression of the nth Dickson polynomial of the first kind. And so it has a nice recurrence relation and with initial conditions 2 and x. But when it comes to explaining the permutation property, the explicit expression given here is not the most important one, the most helpful one. There's an expression called the functional expression and of a Dickson polynomial, which I have not stated here, but that's a more important one. So when a is equal to 0, so Dickson wanted to study the permutation behavior of these polynomials. And so let's fix a at 0. Then what do we have? We have a monomial, and of course it is a permutation polynomial. It permutes the elements of the finite field FQ if and only if n and q minus 1 are relatively prime, because we want x to the n to be a generator of the multiplicative group FQ star. So it only happens when n and q minus 1 are relatively prime, because 0 is mapped to 0. And what about the case when a is not equal to 0? And when a is not equal to 0, so the Dickson polynomial of the first kind is a permutation polynomial if and only if n and q squared minus 1. So q is the order of the finite field, n and q squared minus 1 are relatively prime. So the permutation property of Dickson polynomials are completely known now. They were explained by Austrian mathematician Wilfried Neubauer in 1968. And so permutation polynomials, in particular, Dickson polynomials play a pivotal role in permutation polynomials, which have applications in coding theory, cryptography, and you can even use permutation polynomials to construct Latin squares. And we call such permutation polynomials the local permutation polynomials. So give me a Latin square, I can find a local permutation polynomial that constructs it. And give me a local permutation polynomial, I can construct a Latin square. So there's a one-to-one correspondence between the set of local permutation polynomials over FQ and the Latin squares of order Q. So now the Dickson polynomials, they are well known, and I think they are very well known family of they are a very well known family of polynomials. And so why they are called first kind? Because it was Schur who named these polynomials in Dickson's honor in 1920s, because he introduced another variant of Dickson polynomials, and now we call them the Dickson polynomials of the second kind. And if you compare this explicit expression to the previous one, so this n over n minus I term is missing. And now if you take a look at the initial conditions here, so the second kind also satisfies the recurrence relation, but the initial conditions are different. And studying the so only few mathematicians have studied the permutation property of the Dickson polynomial of the second kind, because it's quite a challenge. To name a few, Stephen Cohen at the University of Glasgow, and Mihai Cipu at the Institute of Mathematics of the Romanian Academy in Bucharest, and then Rex Matthews at the University of Tasmania. They are the mathematicians who have studied, and Robert Colt at the University of Delaware. And these four mathematicians have studied the permutation behavior, but explain the permutation property of the second kind is not completely known yet, because it's very challenging. And I wouldn't encourage any graduate student to take a look at the permutation behavior of the second kind, because as I said, I haven't even seen a paper in probably like 15, 20 years. I haven't seen a paper published about the second kind. So that is completely open. And so we have the first kind and we have the second kind. And then in 2012, Stephen Wang and Joseph Yukas, they generalized Dickson polynomials. They introduced the Dickson polynomials of the k plus one kind or k plus first kind. And so as you can see, if you take k to be 0, you go to the first kind. If you take k to be 1, you get the second kind. So in this paper, they studied the Dickson polynomials of the third kind over finite fields, finite prime fields and finite field extensions. And so they also derived some algebraic properties of Dickson polynomials of the k plus 1 kind. And so now that's the story of Dickson polynomials. So my title says reverse Dickson. So something has been reversed then. So what has been reversed? So we have the Dickson polynomials, and here we have the variable and the parameter. So let's switch them. Let's interchange the role of the parameter and the variable. And it was done by Xiangjung Ho, Gary Mullen, and James Sellers and Joseph Yukas. They introduced reverse Dickson polynomials in 2009 by switching the roles of the variable and the parameter. So you take the explicit expression and you switch a and x. And again, we have the nice recurrence relation. So now, because a main problem in the area of permutation polynomials is finding new classes of permutation polynomials, because they have many applications in the area of coding theory, cryptography, as I said earlier. So they studied the permutation behavior of reverse Dickson polynomials, and it's not completely known yet. And again, similarly, we can define the reverse Dickson polynomial of the second kind. And in the paper, in that same paper, they also introduced the nth reverse Dickson polynomial of the k plus 1 kind. But the authors did not work on the k plus 1 kind in general. So then I saw a couple of papers like about the reverse Dickson polynomial of the first kind and the second kind, and then there was a one on the third kind, then there was a one on the fourth kind. Then I thought, okay, I wanted to generalize everything and unify all the results and bring it to one platform instead of like writing a paper on the fourth kind, fifth kind. So then what I did, I wanted to study the reverse Dickson polynomials of the k+1 kind in general, so that it generalizes already existed results. So as you can see, when k is equal to 0, we have the reverse Dickson polynomial of the first kind, and when k is equal to 1, we have the nth reverse Dickson polynomial of the second kind. And then I showed that, and one more thing to notice here, because since we are in characteristic P, we only have to let k go from 0 through P minus 1. And then I showed that the k+1 kind can be written in terms of the first kind and the second kind. So the advantage of writing the k+1 kind in terms of the first kind and the second kind is when you consider this in characteristic 2, it simply boils down to the parity of k, because when k is odd, then the k+1 kind is simply the second kind. When k is even, it's simply the first kind. So now, from now on, during the talk, I'm always going to be assuming that the characteristic is odd, unless I mention otherwise. So then I wanted to settle down the case where the parameter is 0 first. And so it can be shown that when a is equal to 0, when n is odd, it's 0. When n is even, when the index is even. So we get this monomial times a constant. So there are no permutation polynomials when n is odd. And when n is even, of course, it's a PP, a permutation polynomial, if and only if these conditions are satisfied. And again, from now on, I always assume that A is a non-zero parameter. And the nice thing about non-zero parameters is, then I was able to show that when A is non-zero, you don't have to consider all the values for A, all the non-zero values for A in the finite field. You only have to consider the case A is equal to 1 to discuss the permutation property. And using the explicit expression, you can show that d sub nk of ax is simply this, the right-hand side. So as x varies through all the finite field elements, x over a squared for a fixed a varies through all the finite field elements. So to study the permutation behavior, you only have to consider the case a is equal to 1. So that makes our life easy. And it doesn't happen in Dickson polynomials. And here, so the first one, I showed that the k+1 kind also has a nice recurrence relation, a second order recurrence relation with these initial conditions. And of course, then we have a recurrence relation. So here's the generating function. So the generating function is given by this. And I wanted to explain the cases. I wanted to explain the permutation behavior of the polynomial for several cases where n is a prime power, and where n is a prime power plus 1, prime power plus 2, prime power plus 3. And in the very first project I worked on this, in the first two projects I worked on this, I was able to explain when the reverse Dickson polynomial of the k+1 kind is a permutation polynomial for these indices. And I remember, like after I finished these two projects, there was an AMS sectional meeting at Hunter College, and this is such a nice coincidence. It was at Hunter College in New York, and I attended that conference. It was an in-person meeting. I presented this, and then I received some good comments and suggestions. And one of the suggestions was given to me by one of my colleagues there, Ariane Masuda at CUNY. And they asked me, like, why don't you consider what happens when n is a sum of prime numbers, 3 prime powers? What happens when n is a sum of 4 prime powers? What happens if you generalize it? So then I wanted to generalize this and discuss the permutation behavior. Of course, when you increase the number of prime powers, of course, the difficulty level or maybe the interest, it's up to the individual, may go down. And so now brace yourselves for impact because you are going to be such a nice, beautiful polynomial. So I considered this general case where n is a sum of I number of prime powers. So then I divided everything into two cases. I is odd and I is even. So one may ask, why? How are we going to use this polynomial to discuss the permutation property? Yeah, that's a good question, because uh, this necessarily wouldn't explain the permutation behavior, but it would make any reverse Dickson polynomial enthusiast life easier to take this polynomial and simply consider cases where k is this and n is this, where k is and using several values for k and n. So I consider, and also one thing to notice here, this is something I haven't actually investigated yet, but I think if you take a look at the reverse Dickson polynomials, this term 1 minus 4x always appears. Everywhere it appears. And to point out, it also appears in the generating function of Catalan numbers. I don't know if there's a relationship. I have no answer, but I thought of mentioning it. So this is I is equal to odd, and then when I is equal to when I is even, then it looks very similar. And then I showed that we can also write the k plus one kind in terms of the first kind and the second kind. And again, I showed that some more algebraic properties satisfied by the k plus one kind. So the k plus one kind can be written as the third kind, can be written in terms of the third kind and the first kind. And then I was able to show that the k plus one kind polynomial, the n polynomial of the k plus one kind, can be represented nicely using, it has a nice matrix form, can be represented using this matrix multiplication. And so I wouldn't go into computations. And finally, my results were published in this journal, Contributions to Discrete Mathematics, recently. And so there are too many computations in these results, so I decided to skip. I know that we have come to the last two talks of the day. I know you are tight, so I decided to skip proofs or any computations here. And now I'm going to switch to self-reciprocal polynomials. The reason, I'll explain the motivation behind this. I wanted to classify all the self-reciprocal polynomials from reverse Dickson polynomials, because they have many applications in the area of coding theory. Like, you can use self-reciprocal polynomials to generate reversible cyclic codes. And I do have time. I want to check the time. And so why did I consider self-reciprocal polynomials, and what are self-reciprocal polynomials? So those are the two main questions here. So self-reciprocal polynomials are simply polynomials whose coefficients form a palindrome. Or you can say whose polynomials that are equal to its reciprocal. And given a polynomial, you replace x by 1 over x, multiply by the monomial, whose degree is the degree of the polynomial. And that's how we define the reciprocal. And if the reciprocal is equal to the polynomial, we call it a self-reciprocal polynomial. And as I said, you can use these polynomials to construct cyclic reversible codes. And so what was the motivation behind explaining the self-reciprocal polynomials from reverse Dickson polynomials? So when I worked on the k plus one kind, there were some papers on the first kind, second kind, third kind, and the fourth kind. In every one of those papers, in each one of those papers, they actually wrote the reverse Dickson polynomial in terms of this polynomial f, and then they used the self-reciprocal property of the polynomial f to explain the permutation behavior of the reverse Dickson polynomial. So when I try to generalize everything, I observe that this polynomial f is not a self-reciprocal polynomial for every k. So sometimes it's not. Sometimes it is a self-reciprocal polynomial. Then, out of curiosity, I wanted to see, like, when it is a self-reciprocal polynomial. And then I decided to settle the problem down, and I was lucky. I was able to. And so then I considered the polynomial as a polynomial with integer coefficients. And then I considered the two cases where the index is even and odd. And so here I explained when it's a self-reciprocal polynomial. Then I wanted to go to odd characteristic. I considered this polynomial as a polynomial with coefficients in FP. And again, I considered two cases, n is even and n is odd. And so I was able to classify, give a full classification of self-reciprocal polynomials in odd characteristic. And the last one, the even characteristic. So the self-reciprocal polynomials from reverse Dickson polynomials, arising from reverse Dickson polynomials, are completely classified. And then actually I wanted to stay away from reverse Dickson polynomials for some time, because after all these projects, and then after I went to College of the Holy Cross in Worcester, Massachusetts, and two of my research students, actually, two of my students, they wanted to work on a research project during summer, funded by an REU grant. And so I said, okay, we have this, I've been working on these polynomials. We know when they are permutation polynomials. So if you have permutations induced by a polynomial, so why don't we study the fixed points of those permutations? Why don't we study the cycle types of those permutation polynomials? And then we all decided to investigate the fixed points and the cycle types, because as I said, permutation polynomials have applications in cryptography. So in cryptography, they are more interested in permutations with less fixed points, so they can scramble the message as much as possible. And so this was the beginning of that REU project. And we started with this conjecture that appeared in the very first paper, in which the reverse Dickson polynomials were introduced. And so the authors in this paper, they showed that all these indices are sufficient for the polynomial to be a permutation polynomial, but the other side remains open. So if you want to prove the conjecture, you need to prove that these indices are necessary as well. So then what we did, we actually considered these permutation polynomials and explained, we counted the number of fixed points of these permutation polynomials. So we considered these several cases taken from the conjecture, and we showed that these are the number of fixed points satisfied by the reverse Dickson permutation polynomials from the first kind. And then cycle types. So in this case, cycle types, in this particular case, I would like to emphasize that with this project, with my two students at College of the Holy Cross, we worked on permutation polynomials over FP, over finite prime fields, because the conjecture was on FP. And so we wanted to explain all the cycle types, which are actually partitions of FP. So we again took all the permutation polynomials from the conjecture, and we studied, we were able to explain almost all the cases. There's one case which is not explained yet. If anyone interested, send me an email. I'll be happy to send you the file of these cycle types. And we were able to explain all the cases except one. And so these are the cycle types of reverse Dickson permutation polynomials over FP. And then if you have two permutation polynomials, if you add them, it's not necessarily a permutation polynomial. But if you take x, which is clearly a permutation polynomial, and another permutation polynomial f of x, and if their sum is also a permutation polynomial, we call such a polynomial a complete permutation polynomial, which have important applications in cryptography and digital schemes. And then we also wanted to discuss the complete permutation polynomials arising from the reverse Dickson polynomials of the first kind. And we showed that in that project, all these indices are sufficient for the polynomial to be a complete permutation polynomial. But to prove this conjecture, one has to prove that they are also necessary. So you can consider this conjecture as a sub-conjecture of the previous conjecture. And so far, I've been only talking about permutation polynomials over finite fields, but there are researchers who've been studying permutation polynomials over finite rings because of their applications in coding theory. And we wanted to discuss the permutation property of a finite rings. And so then we showed, we completely explained when when the reverse Dickson polynomial of the first kind is a permutation polynomial over these two finite rings. And then I'm not going to go into details again. So we also looked at the reverse Dickson polynomial of the second kind, and it has a nice recurrence relation. In the same project, we explained the fixed points of the permutation polynomials arising from the second kind. We explained the cycle types, and we explained the permutation behavior of the second kind over finite rings. And we obtained sufficient conditions on the index for the second kind polynomial to be a permutation polynomial of the finite field FP. And it was recently, research results were recently published in this undergraduate journal of mathematics. And so I was at Holy Cross when we worked on this project, and GHE and we were all at Holy Cross. And then now we three are at three different places. I'm at Knox, Hao Ming is at Carnegie Mellon, and GHE is at Columbia. And then before I continue, I would like to acknowledge Xiang Deng Ho at the University of South Florida, my PhD advisor, and Michael Sieve at the University of Michigan, and Ariane Masuda at City Tech, CUNY, and Anthony Rubino at Northeastern University for all the fruitful comments and the guidance they provided me through this all the projects. And I would like to thank them. And so I said in the abstract, I would talk about some open problems. And so here are some open problems. In that project with my two students, we showed that these indices are sufficient for the second kind to be a permutation polynomial. Proving them that they are necessary is an open problem. They are open problems. And then I think 1 minute, something happened. Yes, I think it's good. Yeah, and then two more open problems, because we are looking at bijections from a finite field to itself. So we should be able to find the compositional inverses of these permutation polynomials. And again, consider the ring FPX or FQX, and let's find irreducible reverse Dickson polynomials. Yes, and I'm done. The next slide is, I think, and I'm going to skip this because I think I don't want to go. Do I have 1 more minute, Professor Nathanson?
At most.
Okay, thank you. Yeah, that's all I need. Thank you very much. I'm grateful. And the Dembowski-Ostrom polynomials, I wanted to mention this even though I did not include it in the abstract, because this is a project I concluded with two mathematicians from IIT Jammu in India. So we studied Dembowski-Ostrom polynomials, which have applications in cryptography, and they are closely connected to planar functions, which can be used to construct error-correcting codes. And we completely classified Dembowski-Ostrom polynomials from reverse Dickson polynomials here. And thank you for allowing me to go 1 more minute. And I think I'm done. And thank you very much. And thank you
Thank you
for joining.
Thank you.
Oh, yeah.